Welcome to Brain Vision.
Yeah, so we're looking at solving a question about angular acceleration. So we have a rotating blade of a blender that turns with a constant angular acceleration of 1.5 radians per second squared. We're trying to figure out how long does it take to move from rest, so angular velocity of 0, to an angular velocity of 36 radians per second. So we know that the angular acceleration A is also equal to, or is defined as, the first derivative of the angular velocity with respect to time. This also means that the change in with the constant acceleration, we know that that the acceleration is also equal to the change in the velocity over the change in time between 2 points in time. So therefore, we can see that if we manipulate this equation and solve for time, we see that the amount of time will be equal to the change in velocity, angular velocity, divided by our acceleration. All right, so if we plug our numbers in, we see that we have our change in angular velocity, which is going from 0 radians per second to 36 radians per second. So that'll be 36 radians per second. All right, and we'll divide that by a constant acceleration, which is 1.5 radians per second squared. So if we solve this out, so we just take 36 and divide that by 1.5, we get 24 seconds, okay? So we get 24 seconds. So now part B of the question says, through how many revolutions does the blade turn in this time interval? All right, so if we continue on with our idea that the acceleration is equal to the derivative of the velocity with respect to time, we also know that if we take another derivative of this, we see that acceleration is also the double derivative with respect to time of the angular displacement. So I call it theta. Here, I'm going to erase that. That's a bad theta. So of theta. All right, so we can solve out this derivative, or we can look at our book for our equations. And if we solve this derivative out, we see that our final theta, our final angular position, I'm going to call that time t2, is equal to our original position plus our initial velocity, our initial angular velocity, times our time interval, plus, so when you take that second derivative, you get a 1/2 of the angular acceleration times your amount of time squared. Okay, so again, this is the final, or your second position in a time interval will be equal to your original position plus, here, I'll put some eyes here, your original position plus your original velocity times that amount of time, the time difference between time 1 and time 2, plus 1/2 or half of your acceleration, which is constant over this time interval, times your time squared. Now this becomes, with this situation, pretty easy. So we're looking at how many revolutions. So we're not really worried about where we started at. So our initial position is 0. We started at rest. So our initial velocity, angular velocity, is 0. So 0 times t, or 0 times any time is 0. So plus, so this is 1/2 of a. So if we recall back from our last problem, our acceleration, our angular acceleration was 1.5 radians per second. So that's going to be 0.75 radians per second squared. Second squared. And this is times time squared. Our time, which we solved for in the last problem, was 24 seconds. So this is 24 seconds squared. All right, so when we square our seconds get squared and cancel out. So then we're left with just radians in this. If we work this out, multiply this out, we get this is equal to 432 radians. Now, not quite done yet. So the problem asks for how many revolutions. We're looking at not just how many radians did we travel. So the idea is how many radians are in a circle. So that's 2 pi. So what we do is we were to take our 432 and divide that by 2 pi. Now, in our problem, we only are looking at 3 significant figures, so we don't have to use a super accurate version of pi. But then when we divide this out, we get 68.8 revolutions. I'll just put revs. So 68.8 revolutions. All right. Thank you for watching.